We'll continue our discussion about TCP congestion control today. In the last class, we had talked about some principles of congestion control. So we said that there is this thing called additive increase, where when we don't detect congestion, we try to increase the window but slowly, not too aggressively. And if we have a loss, we detect a packet loss, then we have a multiplicative decrease of the window size. We also said that when you start a TCP connection, you have no idea what the available throughput is. It could be anything from kilobits per second all the way to gigabits per second. So your initial window size, of course, has to be small so that you don't congest the network, but at the same time, it should expand quickly so that you can use the bandwidth. So that sort of contradicts this additive increase idea, where here you only increase linearly. So we said in the additive increase, typically you increase the window size by 1 MSS per round trip time. So in order to increase the window size fast, we said that we start small but we increase exponentially in a phase called slow start. So how exactly do TCP protocols put these together? Now there are various versions of TCP. Some of those were mentioned in the last class. And of course it progressed, it evolved, as people learned more and more about how well different TCP protocols work. They proposed newer ones which had some benefits. So one of the earliest protocols was TCP Tahoe, and a little bit later came TCP Reno, and of course hundreds of different TCP protocols have been proposed after these. So we will look at these three which I mentioned here: TCP Tahoe, Reno and Vegas. And of course in your current Linux machines, most likely you might be using something called TCP Cubic, which is sort of an advanced version of TCP. We will not be looking at it in this class. So let's start with TCP Tahoe. So in TCP Tahoe, we start with a small window size as expected. And so let's say that we start with one maximum segment size. So I'm not going to distinguish between window and congestion window here. Of course, it's understood that the window is the minimum of the congestion window and the advertised window. But for the time being, we'll just assume that the advertised window is really large. So congestion window actually corresponds to the TCP window. And this is time. So what will happen is that this congestion window is going to increase every time you get back an acknowledgement. But I'm just going to skim over that fact that we only increase when an acknowledgement comes back, and I'll show it as if it's increasing smoothly with time. So let's say this is one round trip time and this is the second round trip time. And so on. So what happens at this is 2. So after 1 RTT we reach 2 MSS, and after 2 RTT we go to 4 MSS. So we increase the window size exponentially fast. And let's say that the initial slow start threshold is somewhere here. So we are increasing the window size very aggressively over here, but this is the danger mark. Of course, initially SS threshold has something built in into the protocol, okay, and of course we'll see that this is adaptively varied over time. So let's say that we hit the SS threshold here, and after this we go into additive increase mode. And this phase we said is called congestion avoidance. So the congestion avoidance phase, our window increase is quite slow. It's increasing by 1 per round trip time. So 1 MSS per RTT. Okay, so this is what happens. This is the danger mark. So what happens after some time? Let's say we detect a packet loss, and the packet loss is detected by timeout. So let us say that we set out a particular packet, we set a timer, and we've seen how to set the RTO, I mean the retransmission timeout. So once the timer expires and we haven't got an acknowledgement saying that that particular segment was received, we assume that a loss has occurred. Okay, so loss is detected by timeout, and only timeout in TCP Tahoe. So we'll see more advanced ways of detecting timeout when we discuss about TCP Reno. So here let me just clearly say that in Reno we only detect using timeout. We only detect loss with timeout. I beg your pardon, we in TCP Tahoe. Okay, so in TCP Tahoe we only detect packet loss using time. So what happens here? Since we've detected timeout, TCP Tahoe very aggressively decreases the window size to 1 MSS. So it says things have become really bad in the network. I've got a packet loss, probably some buffer is filled up somewhere. And of course then we want to start out all the way like we did over here. But what should this SS threshold be? And what TCP Tahoe does is it says that things were somewhat okay over here, but I'll be a little bit conservative. I'll reduce it, set my SS threshold to be half of whatever the congestion window was here. let's just call this congestion window, let's say congestion window 0, okay, at this particular point when we saw the packet loss. So we set SS threshold equal to the congestion window divided by 2. So you might say this is being too conservative. Why to decrease it to half? But this is why don't you just keep the SS threshold to this value itself, right? So that there is some validity to that point, because we didn't see congestion up to here and then we saw some congestion here. Okay, but just to be on the safe side, we are somewhat aggressive and we make it half. There is another reason why we might want to make it half, in that actually we may be in slow start when we have a packet loss. I've shown the loss happening here when we are in the congestion avoidance phase, but we could have got a loss here too in the slow start phase, in which case we might have overshot the correct amount we should send data by a factor of 2, because we are exponentially increasing, right? So maybe this is the right congestion window to have, so that we are not just about beginning to congest the network, but we may have doubled. Okay, and so this half factor will help in that particular case. Okay, so we look at that a little bit later when we look at some practical examples. So we've decreased the SS threshold over here to half. So SS threshold was initially, let's see, somewhere here, but we got a loss here and we decreased it to half. Now the rule is that when your congestion window is less than the SS threshold, you are in slow start. When you cross the SS threshold, you are in the congestion avoidance mode. So what should we do here? Well, we should be in slow start again. So we increase the window size exponentially. And then we increase in the additive increase. Okay, this is the congestion avoidance phase. And let's just as an example say that we got a loss here, which is due to timeout. Again, we are going to decrease to 1 MSS. And the new SS threshold is going to be this one. Let's just call this CW1, and this is going to be CW1 by 2. So let's write down the rules. So you initialize the congestion window to 1 MSS. And then what do? We increase congestion window by 1. For each received ACK. And this is in slow start. And once congestion window exceeds the SS threshold, we start increasing the congestion window by 1 per round trip time. And we saw that ends up giving us this peculiar formula. So this is per ACK received. So this is the congestion avoidance. Yeah, and this is effectively additive increase. Yeah, and this would continue, but whenever we have a packet loss, we go back to this particular case. So in either of whichever state I'm in, if I detect a packet loss, what I'm going to do is I'm going to initialize CW to 1 MSS and SS threshold is set to CW by 2. This is the multiplicative decrease. So this is TCP Tahoe in a nutshell. So let's look at a particular example to get an idea of what might happen. So let's just say that we have a source and this is the, let's say, the receiver. And let's say that there's no other traffic on this particular path, just to simplify matters. Let's say that here you have a total of C bits per second as capacity, and let's say that this is much greater than C. The link capacity here is much higher. So this is the bottleneck. So what is going to happen here, suppose we are using TCP Tahoe for communication between these two. Okay, when we are focusing on just the data going from here to here and the acknowledgements coming back from the receiver to the source. In practice, of course, a TCP connection is two-way and you can have data going in both directions. So let's see what the congestion window might be over time. So the congestion window starts at 1 MSS. And let's say we are in slow start. Let's say the SS threshold is quite high initially. So we are in the exponential phase. And let's say that at this point, suppose this is CW0, or let's say just CW dash, and we are assuming that CW dash divided by the round trip time is roughly equal to C bits per second. So this C is the capacity. Okay. So what is going to happen when we send out a window size this big? Okay, so effectively what is going to happen here, if we look at the queue over here, the output rate is C bits per second and our input rate effectively equals C bits per second, okay, at this particular point in time when the window size is CW dash. So what happens is that the queue starts filling up once the window size goes beyond this. Okay. And what happens is that we are in an exponential phase. We are rapidly increasing the window size, and let's say that the queue builds up, and that's when we have packet loss. and let's say a timeout occurs. And because of that, window size is going to decrease drastically to 1 MSS. So this is what we would expect, and we didn't even have time to get into the additive increase, which is what I call the congestion avoidance phase. When we were in slow start itself, we got a packet loss. And here you see it makes sense to have SS threshold equal to half this particular congestion window. Because here we were increasing very fast. We said that this is the appropriate congestion window size. Okay, we just sort of be filling up this pipe over here. And we are doubling every round trip time. So it's possible that we may have actually gone twice beyond the appropriate congestion window size. So we want to set the new danger mark equal to this value. So what happens now is we are going to increase the window size. So possibly this is a little bit high for this diagram. So half of this might be, let's say what, here. And we would go into the additive increase phase of it. And now of course we are not inducing much congestion because of this additive increase. It's very slow. And let's say here we fill up the queue, and then we have a packet loss. So if I were to plot the queue size over time at that particular queue shown, queue size is essentially the number of bytes in that queue, and initially we are low, but once the input rate exceeds the output rate, we are going to increase. And let's say we reach somewhere here, and then let's say that this is the maximum size of the queue. So we hit the queue round about this point in time, and the queue fills and we get packet loss. But then since we've decreased the window size quite drastically, you would expect the queue to rapidly decrease. And then again, when we, let's say we cross this danger mark somewhere here, I'm saying that this is CW dash. Again the queue starts increasing, and then we would see the queue getting full. We see packet loss, and then of course the queue decreases. Right, so this is how TCP works, and TCP is not directly communicating with the router. The router is just trying to do its best to forward packets, and TCP is inferring indirectly from the acknowledgements and things like that whether a loss has occurred or not. So this is how a single TCP would work, TCP connection. In practice, of course, the situation is much more complicated. There could be hundreds of different TCP flows going through the same bottlenecked router. And of course, lots of research has been done to analyze what happens in those sorts of situations, and it's a non-trivial thing to analyze, because it's a distributed system. There's no sort of coordinated feedback taking place. In fact, it's possible that when the queue is full, that some flows packets are lost, but other flows packets are not lost. That too might happen. But let's look at another example, a little bit more complicated than this, but at least maybe not too complex, but as you see, things will become non-trivial when we have more than one flow. So suppose we have an example with two TCP Tahoe flows. In this example, let's say that we have a sender here, or a source, and let's say that we have a receiver, one, and let's say that there is a second source and a second receiver. And both are using TCP Tahoe. And of course the capacity is C bits per second. So now what's going to happen? So let's say that first this TCP starts, and then maybe a little later this one starts. Okay, so let me plot the window for the first TCP connection. So this is from source 1 to receiver 1. So let's say that we were in slow start, we got a loss, we decreased the window size like earlier. This time we went into congestion avoidance, we got a loss. So these are all timeout losses. Decrease the window size to 1. Right, and this happens, and so on. So the SS threshold is changing. Maybe the SS threshold was here, and it decreased. So this is the SS threshold, and this is the new SS threshold. So every time we get a packet loss, we just set SS threshold to be half the congestion window, and we decreased it to 1. Okay, and let's say we were in additive increase phase here, and now the second TCP starts. So this is source 2 to the receiver 2. So the TCP starts over here. It starts transmitting data. So this TCP is in slow start, so it starts with 1 MSS. So here we are in slow start, remember, and already this TCP flow is sending at quite a high bit rate. It's almost filling up this particular queue over here. Right? So we have to look at this particular router. This is where the queue would be filling up. This is the output queue at this particular link. So already it's almost filling up the queue with that particular window size, and then this goes in slow start. Very rapidly increases the window, and the sum of these two is enough to exceed the output link speed, and this causes a loss. So let's say both of them have a loss here. Okay. So what's going to happen here in this particular case, both are going to decrease their window sizes, and the SS threshold is going to be here for this one. It's going to be half of this window size. Here the window size hasn't increased as much as over here, so the SS threshold is going to be lower. And again we go back here to window size 1, and we are in slow start, but then we are in the additive increase over here. So here we are in slow start. So in this particular case the SS threshold is a bit higher, so our window size goes up, okay, all the way up to the SS threshold. We quickly go there, and then we go into the additive increase phase. Okay, so what happens, let's say somewhere over here again we have a packet loss. And to simplify things, let's assume both have a packet loss, and then we again go down to slow start, and somewhere else we have a new SS threshold. Okay. And the SS threshold might come down here. Right. So depending on when exactly you get a packet loss, the SS threshold is going to change. Okay, so notice that in this particular case both had a packet loss, but the window size after that was not the same for both of them. Both of them of course decreased the window size to 1, but the SS thresholds were different, because when the loss happened, this one's window size was larger than this one's window size. So the SS threshold was higher for this flow. Okay, so this flow was in slow start for longer, and it sort of had an advantage. It had a higher window size than the second flow. What might happen is that it's possible that this one has a loss, but this one doesn't have a loss, and that could happen. So if you look at this particular queue, I'm just zooming into the queue over here. Let's say that for flow 1, okay, we have something. Let's say that flow 1 has, let's say this is the maximum size of the queue, and there was a packet of this flow which couldn't fit in, and so this was lost. Whereas there were other packets, let's say from the second flow, and these fit in the queue, okay, and it's possible that the queue emptied a little bit, by the time the next packet came from this second flow. So it's actually possible, and you can even do NS simulations if you want to see that this might take place. it's possible that you may have some packet losses, but only one flow or a subset of flows entering this queue will lose packets and other flows get through. Okay, that there is no packet loss. Okay, so what I mean is that this packet was lost because it hit a full queue, but by the time, let's say, another packet from flow 2 came, this is the same queue, I'm just showing at a different point in time. What might happen is that we reach this sort of situation where the queue has already emptied a little bit. So when the next packet from this flow 2 comes, it actually has space, there's actually space in the queue for it to enter. So those sorts of tricky things might happen, and in this particular situation, this would decrease to 1 MSS and it would set the SS threshold appropriately. This one didn't have any packet loss here, okay, so it may increase the window size and it may have a loss here, right, and then it would decrease. So I'll just say no loss at this particular point in time, okay, but a loss happened here. So it's very hard to predict exactly what's going to happen when you have a multiple TCP flows going through the same bottleneck. And of course, the situation gets more tricky in the real world because, I mean, it's not just 2 flows, you could have hundreds of flows. Plus, you may have different bottlenecks. Why should there be only one bottleneck? There could be multiple queues on the end-to-end path which are losing packets. Okay. Also, the round trip times of these different TCP flows will be different typically, and people have done TCP modeling to show that actually affects the throughput. If you have a smaller round trip time, it's to your advantage. Okay? It's just the way the modeling works, because essentially the slope is 1 MSS per round trip time. So if your round trip time is smaller, then effectively the slope in the additive increase mode is different for different RTTs. Let's try to understand the whole phenomenon of stop and reload. So many times you might have been downloading a web page and then it stalls due to some reason. So you get a bit irritated and you hit stop and you just hit reload again on the browser, and then it comes up in a flash. So why might that happen? So we look at one possible reason over here, and let's suppose you were using TCP Tahoe. We'll see what might have happened. Okay, so the web page is slow, and you hit stop and reload, and it sort of downloads fast. So suppose this is the congestion window size and this is time, and let's say you sent out the first packet and this was lost. So what is going to happen over here? So this was my packet loss, and so what are we going to do? So of course I didn't describe it over here exactly in fine detail, but there is going to be a minimum SS threshold. Okay, so let's just say that minimum SS threshold, let's say, is equal to 1 MSS. Okay, of course we are assuming that it's greater than 1 MSS. So what happens is that initially your SS threshold was large, but then after one round trip time you realize that this acknowledgement didn't come. Okay, so actually your timeout might be quite large. Let's say that this is your initial timeout. So you sent out one packet and then you saw that there is no acknowledgement coming back. So what happens? So now again you have to go back to slow start, but your SS threshold is going to be 1 over here. So normally you should set it to be half of this, but we said there is a minimum value that we allow. So we set SS threshold to 1 MSS. Okay, so what I mean is it is minimum of 1 MSS and congestion window by 2 at the time you had a packet loss. So now we are in a bit of a fix. So we have window size 1 MSS, but now we are in additive increase mode. So we are nowhere in slow start. So maybe there is a lot of bandwidth available, but we were a little bit unlucky, and our first packet itself which we sent out got lost. So we are in the additive increase phase. Okay, so what's going to happen is it's going to take a long time for the file to download because this 1 MSS may be too small. Okay. So what we might do is we get irritated. This is very slow. So what we do is we hit, let's say we get irritated and we hit stop and reload. Okay. So TCP is going to start off again. So it's like you have a new TCP connection effectively. Okay. And so again we start at 1 MSS. Let's actually draw it on another graph just so that it. So what happens here is again we start at 1 MSS and our SS threshold is high, and we go in slow start and then we hit the additive increase phase, and there is no packet loss. So we've reached a much higher window size much more quickly, okay, than we had over here, and the download completes over here. So this phenomenon might be occurring even if you have something like TCP cubic working. It's just if you're a little bit unlucky and that initially lots of packets were lost, let's say. Okay, you were unlucky and then you went into congestion avoidance immediately, even when your window size was 1. Okay. So this is an example of what might be happening. Of course, the actual situation might be a lot trickier, but it's a good chance that you were unlucky somewhere and you had a lot of packet loss. So this is TCP Tahoe. We have slow start, congestion avoidance, and if you have a loss, you decrease your window size to 1 MSS. So people were thinking, does it make sense to do this? So questions that people asked is, do we really have to reduce window size to 1 every time we have a packet loss? That is very drastic. Should CW equal to 1 MSS after a packet loss? So definitely this is a conservative way of doing things. I mean, the queues will relax if everybody decreases their window size to 1 MSS. But can we do something maybe better, maybe not so drastically decrease the window size? And also, can we detect loss in other ways? So people did come up with these answers for these questions. Yeah, and so first let's look at this second point. And there were some enhancements made which went into TCP Reno. So the first enhancement is called fast retransmit. Okay, so this is actually answering the second question. So let's say that this is the source sending to the receiver. And these are the packet numbers. So actually you send out sequence numbers, you don't send out a packet number. But just for simplicity, let's say that we mark these as 1, 2, 3 and so on. So these packets are going across, and let's say this third one got lost, and it's possible that these managed to get through because maybe the queue was full when this packet hit the queue, but the queue relaxed a little bit when 4, 5 and 6 hit the queue. So we are using the cumulative ACK. So remember, when you send an acknowledgement, you're saying that I got everything from the beginning up to that acknowledgement number -1. Okay, so basically you're saying that I'm expecting this particular byte after that. So what is going to happen here? You're sending back an acknowledgement for this one, this particular packet, or so actually let's say that this is byte 1, let's say, and this is byte 1000. Let's instead use the sequence number and not packet number, just to make it more realistic. This is 1001. Let's say that there are 1000 byte packets, 2001, 3001 and so on. So what is this ACK going to say? This is the ACK for 1001. This is saying that I got everything from the beginning, and it has the ACK number. (2001). So it's saying I got everything up to 2000. So these are 1000 byte segments. Now this was lost, and so we're going to say we are going to send out acknowledgements, but they are going to have these numbers. So this is going to say 2001. I got everything from the beginning up to 2000. And similarly this one too is going to say 2001, and this is also going to say 2001. So the rule is every time I get an acknowledgement, I will send out, every time I get a data packet, I will send out an acknowledgement. But the acknowledgement number I'm allowed to send out is only up to that point where I've got all data from the beginning. Okay, so the largest sequence number up to which I've got all the data. So it's going to be 2001 for all of these. Okay. So now this is giving us some information. Okay, so these are the normal ACKs, and these are dupacks, which we've discussed in an earlier class. So they are duplicate ACKs. Duplicate ACKs of this one. And this conveys information. So what researchers said, whenever you get 3 duplicate acknowledgements, then what you're going to do is you're going to assume that there was a packet loss. So the fast retransmit rule. So retransmit segment with sequence number 2001. If there are 3 dupacks received for it, received let's say with sequence number 2001. Okay. So what you are allowed to do, what you can do here, you can retransmit this segment with sequence number 2001. So that is this particular one. Okay. So this is considered to be a sign of packet loss. Okay, because clearly something is wrong. I mean, clearly this one didn't reach. I mean, receiver was saying I got everything up to 2000, but clearly this one hasn't reached, because otherwise the sequence number would have, the acknowledgement number would have increased to 3001. Okay. But this is telling me that some packets got through. Okay. And because of that, thanks to those data these particular segments getting through, I am getting back acknowledgements. So of course this is a different way to detect packet loss. So this is a new way to detect packet loss. And this is called the triple duplicate tags. So you might say, why do we have to wait for 3 duplicate acknowledgements? Couldn't we have just assumed that the packet was lost when the first duplicate acknowledgement came? So in this particular diagram, yes, but that's not always necessarily true. So suppose this particular packet hadn't been lost, suppose it was just delayed. So this hypothetical situation, let me just put it in a different color. So instead of packet loss, so suppose it was delayed like this. Okay. Then what would happen? So in this particular situation, this particular segment would reach before this. There could be packet reordering in the network for some reason. And then you would send out a duplicate acknowledgement, because I didn't get this. But of course, as soon as this one reached, I would send the appropriate acknowledgement number. Okay. So what the researchers said is that because of packet reordering, I may actually get one duplicate acknowledgement. Okay, but they said maybe the packet reordering is not so drastic in the internet for 3 duplicate acknowledgements. So if I get 3 duplicate acknowledgements, I am more confident that there was actually a packet loss rather than a packet reordering. Okay. So the thing is, TCP is going to take some drastic measures every time you detect packet loss, which is why you don't want to without good reason say that there was a packet loss. Okay, for timeout we said we are decreasing window size to 1 MSS, and we'll see what we do here. Here too we decrease the window size drastically. Okay, so you don't want to be rash and for a single duplicate acknowledgement say that there is a packet loss, because it just could be that one of the packets was delayed more than the other ones. So what do we do in fact when we detect packet loss because of 3 duplicate acknowledgements? And that is called fast recovery. So this is what we do when loss is detected due to 3 duplicate acknowledgements. Okay, this is not for timeout. For timeout, I'll just put it here. For timeout loss, congestion window is set to 1 MSS as in Tahoe. Okay. So what are we going to do here when we get a packet loss? Let's say that this is the congestion window and this is time. Let's say we have 3 duplicate acknowledgements here, a loss detected due to that. Let's just call this particular location CW0. So what we do is we decrease SS threshold like before, CW0 by 2, but we set congestion window equal to the SS threshold. So we skip the slow start phenomenon and we go directly to the congestion avoidance. Okay, but we don't decrease the window size to 1. Okay, and we increase the window size in this way. So let's see. So we increase the window size and the SS threshold is set to this value. So this is a fast recovery. Instead of going to congestion window size of 1 MSS, we start at congestion window by 2. Okay, and since it's already equal to the SS threshold, we are in the AI mode again, straight away. Okay, so this is a better, otherwise again we have to start from 1 where we are very slow and we go into slow start and so. Okay, so it's called fast recovery. So the window recovers faster than earlier. Okay, but just to reiterate, suppose I have loss due to timeout here, I will actually go back down to congestion window equal to 1 MSS. Okay, and of course SS threshold is set to be half of this. So we start in the slow start and then we go into the additive increase mode after crossing the SS threshold. So why do we do things differently depending on what type of packet loss is detected? So the reason is that, see, in this triple duplicate acknowledgement case, definitely some packets are getting through even after you get a packet loss. Right? So because after all, duplicate acknowledgements are signaling that some packets are getting to the other end. So the intuition is that the congestion is not too severe. Maybe one packet was lost because it was unlucky to hit a full queue, but maybe the queue has relaxed a little bit, which is allowing more and more packets to get through. So we do relax the window size but don't decrease it so drastically. Now when you get a timeout loss, that means you didn't get triple duplicate acknowledgements. Okay, because when you get triple duplicate acknowledgements, you anyway retransmit the packet, right? Like we saw on the fast retransmit, and you sort of disable the timeout value. Okay, so I should say that retransmit that segment and disable old timer for the first. What I mean is, for the first time you sent that sequence number, that particular segment out, you disable that time. Okay, so whatever timer was set for this is disabled, and of course you would start a new timer for this particular sequence number now, okay, depending on when you sent it out. Okay, so timeout loss means that you aren't getting duplicate acknowledgements which would have stopped the timer. So if you get a timeout loss, you assume that things are very bad compared to this situation, and so this is assumed to be worse than the 3 dupac case, which is why we decrease the window size to 1. Okay, so timeout is always bad, and usually when your download stops due to some reason, probably a good reason is that you had a timeout. Okay, and the situation is quite bad. Right? And so this is effectively what we do in TCP Reno. So TCP Reno, it includes fast transmit, fast retransmit, and fast recovery. Okay. So in the next lecture we'll talk about TCP Vegas. And what TCP Vegas is going to do in addition to this is that it's actually going to look at the measured round trip times. Because after all, we said that round trip times can also give us information about queue sizes building up. So maybe we can, even before a packet loss occurs, we can take some action to decrease the window size so that there are fewer packet losses in the network. So we'll look at that in the next lecture.